Hello everyone, my name is Shaohuai Shi from Hong Kong University of Science and Technology. Today it is my honor to share a work accelerating distributed K-FAC with smart parallelism of computing and communication tasks. This is a joint work with my colleague Zhang and Body. I will share my talk in several parts. So it is well known that synchronous stochastic gradient descent method has been widely used in training deep learning models using multiple processors. However, actually, it has two main limitations of SSGD. Firstly, it requires a large number of iterations to converge. Secondly, it is very difficult to optimize large mini batch size. So recently, the second order optimization techniques has been brought into the optimization of deep learning models. Particularly, it utilized the Fisher information matrix to precondition gradients than this form. So it tries to use the inverse of the Fisher information matrix to accelerating the training with a less number of iterations. For example, in ResNet 50 model, you just need to train 30 epochs with even with a very large mini batch size. So among this second order optimization, the Kronecker factor approximated curvature method is one of the efficient approximation of Fisher information matrix. In K-FAC, actually, it tries to approximate the FIM as Kronecker products of small matrix. And A and G are the activation output and the gradients of a particular layer. With these two kinds of information, we can construct the Kronecker factors, capital A and capital G. With these two capital Kronecker factors, we can construct the approximate Fisher matrix. And then using its inverse to precondition the gradients to update the model parameters. So when we utilize the multiple GPUs to train the K-FAC, actually it changes this update formula to this formula. So we can compare the distributed training using the first order method and the second order method in details. Actually, the distributed K-FAC has three main differences with the SSGD. Firstly, it needs to construct the connector factor A and G, which are some computation tasks. And secondly, it needs to aggregate the gradient, the results of the connector factors A and G from multiple workers, which are some communication costs. And thirdly, it needs to inverting the matrix A and G before precondition the gradients, while the matrix inverse is extremely slow. So existing methods try to optimize DK-FAC with some concept of model parallelism, which using multiple GPUs to calculate the gradients, the inverse in parallel. So for example, using P GPUs, first GPU can calculate the first layer, the second GPU can calculate the second layer, and so on and so forth. So that each GPU only calculates several layers results. And finally, every GPU will get the results from all the other GPUs. However, we claim that such kind of optimization method is suboptimal to utilize the training efficiency of the clusters. So we analysis the training procedure of DK-FAC with a DAG. So compared to the SHGD, actually DK-FAC introduced several different things, including constructing the connector factors, communication connector factors, and also do the inverse computation, and finally get the inverse results. So we propose a solution to improve the training efficiency of DK-FAC named Smart Parallel DK-FAC with two main techniques. The first one, we try to alleviate the communication overhead of aggregating the connector factors by pipelining technique. The second main idea is to minimize the overhead of inverting connector factors by balancing the workloads in multiple GPUs, considering the communication cost. Regarding the pipelining technique, actually during the feed-forward computation, the connector factors has been, once the connector factors A has been calculated, and then it can be aggregated with other workers directly, so that the communication A can be overlapped with the computation of its next layer. So it is the same during the backward propagation for constructing the matrix G of it and also its communication. So when we utilize the pipelining technique, we also need to address the tensor fusion, the latency problem of small tensors. So we use the tensor fusion technique to reduce the communication overhead of the latency sensitive small tensors. And we utilize the optimal tensor fusion solution by determining which parts of tensors should be fused, while the other parts of tensors should not be fused to achieve a better iteration time. So regarding the distributed inverting connector factors, we try to propose a load balancing solution, and also we need to trade off the communication cost of communication and also the computation cost. So we formulate this problem as a general optimization problem. We will not go to the details due to the time limit. We can go to the paper for details. So the key idea is that we need to modeling the communication cost and computation cost with respect to the dimension of tensors so that we can place different tensors in different GPUs so that multiple GPUs have a very load balancing workloads. And also, we need to determine which parts of tensors should be distributed into multiple GPUs, while which parts of tensors should not be distributed to multiple GPUs, so that we can balance the overhead of computation cost and communication cost. So we built our prototype system on top PyTorch and Hoverboard. So we conducted our experiments on 64 GPU cluster connected with 1 gigabit infinite band network. So we measure our performance in 4 popular convolution neural networks. So this is the end-to-end performance comparison. Our method, SPDK-FAC, outperformed existing methods about 10% to 35%. So we also break down the time performance to make a better understanding which parts of benefits has been utilized by our different techniques. So here comes to the conclusion. We first try to analyze the problem of the distributed K-FAC and propose some solutions. And actually, this kind of distributed training of DK-FAC has some limitations. For example, the inverse computation is very slow and the communication traffic is also very high. So it is also very important to optimize this kind of problems to propose a better solution of distributed training of K-FAC so that it can be more practical in deep learning applications. So that's all for my work, and thanks all for your listening.